Hi, this is your TA Asif. Today we're going to talk about the Lab 6, which is level detection, and Lab 6 is also your final test. This actually is the last lab of this semester. So, in the introduction, we need to discuss like why we need to detect the levels. Like when you are doing something, you need to control your forces to the system. By that I mean, for example, you are controlling the temperature of an oven. Okay, so you see, like here is a set point. So when you see you have reached this point, and you see, okay, I have provided enough heat, I should turn off. And when you cool down, you might need to get back when you go below your set point. But if we expect this kind of results, we are thinking an ideal signal and ideal control, but that is not the real case. The real world signal is something like this. So it will just fluctuate, go up and go down. There will be glitches and noises. There should be spikes, and it will just keep your heater turning on and off. If you see here, you see if we expected this kind of behavior and we encountered this, so your heater will be turned off, turned on, then off. So you have some problems in this region. Like we don't want your heater to turn on and off repeatedly again and again. So that might cause some problems. To solve this problem, we use a very simple comparator circuit. So your output should be plus Vs when Vin is smaller than reference, and your output should be minus Vs when your Vin is higher than Vr. So this is how it works. Like if you think about the op amp, it's an comparator. So you can just build this circuit with this very simple circuitry. But this works only for ideal world signal and the mathematical models, and is almost never used in practical application. The reason we just mentioned in the last slide. So we actually want transfer characteristics something like this. So if you remember, this kind of things are called the hysteresis loop. Like they go up and down at different points. Like if you think about the output voltage and input voltage, so if you start going this way, you are high. Okay, it's also red, so we can draw here. So you are going on and on and on, and when you have reached that positive threshold, here you go low, I mean the minus Vs. And if you drop back, I mean if you drop lower than Vt plus, you don't switch high. You keep waiting, and when you reach that Vt minus negative threshold, then you go high. So these are the hysteresis loop. We have seen them in different occasions in magnetics and many other applications. So we know what it is, but they have some criteria. Like every hysteresis is defined by these three terms. Like you have a positive threshold, you have a negative threshold, and you have the output saturations like the plus Vs and minus Vs. However, one important thing is the window must be bigger than the noise. Like if your voltage is, input voltage fluctuates like this, this is fine because your window is big. But if your fluctuation is like this, what will happen? Like turn on, turn off, it will just go on. Alright, so if you know you are going to have some noise, your window has to be bigger. So here is the Smith trigger circuit. We are going to use the window switching instead of level switching. It is open loop. V plus has two levels depending on the output, and reference voltage cannot be used to adjust the levels. Here R3 output impedance is op amp. It's very important here. I mean, we have drawn this R3 separately, but you actually don't have to put it in the circuit. It's inside the op amp. So it's just like we're just drawing it outside so that we can tell, okay, this is the output impedance of this op amp, and it can be found from the data sheet. So actually your op amp box includes all this. Okay, so R3 is inside the box, it's not outside. So here is the analysis. So the output saturates either at the either rails. That means either it goes high or low, and circuit working in open loop, and gain is very high, and turn on and turn off voltages are determined by analyzing the circuit. So here are the outputs, and the equations are pretty similar to the ones we did before for the open inverting and non-inverting amplifiers, but this time they are open loop, and we have something more here. So anyway, so this is the equation that defines your Vt plus, and here is the equation that gives you Vt minus, and the width is this. So V0 plus and V0 minus are the levels at which your op-amp's output will saturate in positive and negative direction. That means this term and this term, they actually define when you will be switching. So that means V0 plus and V0 minus is here. Sorry, the Vt plus and Vt minus is here and here, and these are the output saturation and output saturation in the negative way. So this is the hysteresis loop that we saw before. Now here is the design goal. First, you have to use a square wave. That's the first stage. So you can get it from the FGen, no problem. Half millisecond, that means your time period is 1 millisecond and you have 1 kilohertz signal. And from that you have to generate a triangle, the triangular wave. So the easiest way to do is to integrate, like you have used an integrator before. So you will get something like this. So from here to here, integrate. You got the sort of. After that this is your final output. So if you look carefully, when you cross 5, you go, you're 0, 0, 0. When you just crossed 5, you go 1. When you cross 5 back again, nothing happens. But you cross 4 here, then it goes back to 0. The same thing in negative cycle, nothing happens, and here you go 4, nothing happens. You go 5, it goes back to 1. You go 5, nothing happens. You go 4, it goes back to 0. So simply speaking, it's you turn on when you cross 5, but you don't turn off until you get below 4. Okay, so that's the requirement. So from this stage to this stage you get by simply integrating. It's very simple. So here are some additional specification. The supply rails should be equal or less than 10 volt, output resistance should be 50 ohms, output voltage should be 0 to 4 volt. That means here this is 0 volt and this is 4 volt. So your amplitude should be 4. People actually don't get 4, sometimes people get pretty close to it, but that's fine. If you get close to 4, that's okay. And then you have to get the output impedance requirement is optional. If you can generate the output, that's okay. You don't have to match the output impedance requirement. Small output impedance is required to drive load. Design the circuit first, complete the simulation and test the hardware. Concentrate on meeting the main design specs shown in the figure in the last page. That means if you can't get an exact output, but try to meet the basics first. For example, try to get your triangular wave in the right shape first by integrating. After that, you see that if you can switch in different levels. Like if you switch up and down at the same level, that's not going to work. So if you can establish all these requirements by some degree, that's okay. You don't have to get it perfectly, but you should be in the neighborhood. Okay, so that's the additional specification, and mathematically speaking, you should come to the lab with values of this, and this, like what kind of threshold plus, threshold minus, and width you expect. And just as I mentioned before, R3 is already inside your op amp, because I'll give you the slide so you can read. So you cannot change its value, so you should consider it in your design, but you don't need to add it. And also do not add R3 in your SPICE, because when you put the op amp inside, SPICE thinks okay, the R3 is inside it. You don't have to put it separately. And this is how you can create a triangular pulse in SPICE. Like if you want, you can just define the terms, rise time, fall time, and using the piecewise linear source. So this is a general block diagram, like what is expected. So square pulses, this is provided from your board. Then you build the integrator, you get the triangle wave shape, check here. So at first what you should do is like probe here with oscilloscope, probe here with oscilloscope. So you put the squares, you get the triangles, then you get the Smith trigger, wave shaping circuit, impedance matching circuit if you want, and then you have the final output, which is something like this, and off and something like this. And on your testing hardware, you are allowed to use plus 15, minus 15, plus 5, plus VPS, and this, except the square pulse. Any questions?
So you're saying we do get like the function generator for the square pulses?
Yes.
Okay, I'll let you know.
So I'm going to repeat it once again. It's very simple. The thing is, you get the square, you make triangles. From the triangles, you turn on 5, turn back off at 4. That's it. So you just have to integrate and use the Smith trigger and wave shaping thing, and then you get the final output.
Okay.
And you can see the datasheet of this. They might come handy. And yeah, this the slides we have. We used materials from all these places. So any questions?